In this session, I'll be talking about design of experiments, or DOE, its creation and analyses. So the end of this session, you'll be able to create two-level full factorial experiments addressing two-factor interaction consideration. You'll look at both saturated designs and explain the DOE fractional factorial design alternatives. So this is where we're at in the overall roadmap. Design of experiments is one part of the make improvement process. This is the portion of the design of experiment steps in the overall roadmap that we'll be talking about. There's some more drill downs available in Lean Six Sigma Project Execution Guide, and we're basically walking through the implementation of those steps. So why do design of experiments? Well, within the make overall project execution process, we're really looking at improving a metric. That's what we focus on in the integrated enterprise excellence approach. So the non-conformance rate in this example is not performing as well as we like, so that metric pulls for project creation. We can then do various hypotheses tests using in the region of stability. Wisdom of the organization inputs can help us determine what we're going to look at. And we also can look at the 30,000 foot level transition because of an improvement that we've made. And we're going to be focusing again on design of experiments. So just to reiterate, at a high level, 30,000 foot level view is what we have. We'll look at how we're performing. We're saying it's not as well as we like. It pulls for project creation. We found some factors in the DOE that could improve our process. We implemented those. Our process changed and enhanced level of performance. And now we've got the benefits of the execution of this project. So in design of experiments, we have basically factors and we have trials. So in this case, we're looking at three factors. We're calling them A, B, and C. Could be temperature, could be high and low, could be sheen high and low. It could be department 1 versus 2. It could be speed, could be high versus low. So these are the type of things that we might consider. The application of these techniques are useful in manufacturing, but they're also viewed as a transactional process. So notice each factor has a high and low level. So we're talking about this as a 2 level. So we take those on as +1 as a -1. So for example, A might be department 1 if we call it plus, and it could be -1 would be department 2. The idea is then you would run each of these 8 trials and you get these responses shown on the right side. So in this case, we have 8 responses. So again, we have plus or minuses to designate which our factors are set at. So we'll notice we have the equal number of pluses and minuses. The estimated factor effects can be assessed by knowing the difference between the average output of the trials. So for the case of factor A, we'd average high values of A versus low values. And we look at the difference. That's what we'd estimate as the effect of factor A. So we can do that for the other particular factors together. Now the way we look at interactions, that's working together, that affects our response. Maybe temperature and humidity work together to affect the overall response. So the way we do that is we multiply the columns together. So for example, AB, we multiply it together, we get the column AB. A times B a plus, we get a plus there. A times B is a minus, we get a minus there. So you notice we have an equal number of pluses and minuses. We also have a 3-factor term there also, where we multiply all 3 of them together. Now the way we see if or assess whether there's a factor that's significant, we again look at the high versus low. and that's an estimate of the effect of that interaction. The question is whether the difference is large enough to be considered significance. So if we were to plot out a factor that's significant, we would see non-parallel lines. So you can see we're looking at, for this case, A and B, where we have 4 different combinations. And you notice, for example, a B plus and A plus, that would be the averaging of the 2 trials that are both high, and looking at those values, that's where you get that value. So that's what we're going to be looking at. Now the question is those effects significant relative to error? So this just describes showing what that each of those points would be. So if there's no interaction, then the lines are parallel. And so again, we want to assess whether the out of parallelism is large enough to be considered significance. Now, if we were to have factors that are noise and the other factors are not noise, the question is, where would we put the factor level? So let's say we're not interested in so much the magnitude of the response, but we're interested in decreasing variability. So in that case, we'd have A high, and we'd also have, if A is a factor that's not the noise and B is a factor that is the noise, then we want to set factor A, because then the difference between B high and B low is smaller. So when they got many factors are considered, full factors can have a large number of trials. So for example, if you got 7 two-level factors, it'd take 128 trials. So that's beyond what most people can afford in an experiment. So the way we get around this is we run fractional factorials. In this case is what I call a saturated fractional factorials. So before we were running factor A, B, and C and looking at the response, but now we can run 7 factors and they would have the combinations noted below. So now, for example, in trial number 2, before we had A high, B high, and C low, we got a response and a full factorial. But now for this 7 factors and 8 trials, we really have A high, B high, C low, D high, E low, F low, and G low. So then we get a response X2. So the disadvantage of this is we got what's called confounding. So you can see, for example, AB is confounded with D, because you simply do the arithmetic like we did before for the 4th column in, but now we don't know if it's D or AB. Now, if I'd like for you to stop this recording and look at tables M1 to M5 in the back of the book, and also N1 to N3, what those tables describes, M tables describe various designs that you can have, and then tables N1 to N3 describes the various interactions that you can have. So it made it be hard to believe, but even if you got 7 factors in 8 trials, that there's no way that factor E could affect the overall response, or A could affect the overall response if factor E is significant. To illustrate that, I'm going to be taking A to be or E to be high, so you can see I put, whenever it's high, I put 500. Therefore, then we're going to see if it's significant or not. So factor E, we look at it, it shows the difference of 500, which is what we input it as. But if we look at the effect of A, we see that it turns out to be 0. So even though we had 7 factors in 8 trials, there was no way that if one of the factors is significant by itself and not interaction, but by itself, there's no way to affect our decision about the other factors. So mathematically, this is kind of what we have when we look at factor A and B, or A and E. So this example that we're going to look at now looks at a saturated fractional factorial. Purpose of this illustration is all that main effects will not be confounded with the other one. So we have also other factors, possible combinations. So for factors, A trial, we have 3, and we could have up to 7 factors in 8 trials. For for 8 trials and 2-factor interactions, we can have between 3 and 7. We could have in the case of 3, all interactions are determined, but 7, 2-level factors, saturated factorials, 2-level factor combined with main effects. If we have a resolution is designated by 5 plus, then it's a full factorial. If it's resolution 3, we got the main effects are confounded with the 2-factor interactions. However, there are other choices that I mentioned here, and we designate those as resolution 4 and resolution 5. So resolution 4 is basically got 2-factor interactions combined with others, but not the main effects. Resolution 5, 2-factor interactions are not combined with 2-factor interactions are the main effects. So table M shows the various resolution alternative for the number of factors, 8, 16, 32, and 64 trials. Where with the IEE approach, with doing design of experiments, we only look at 2-level factors, and it's 2 to the n. So it's 8, 16, 32, or 64 trials. We don't do other trials such as 12, 24, and so on. These Plackett-Berman designs or other designs don't have a clean interaction assessment. So we can do some great, wonderful things if we do 2 to the n that's described in the book. So this is what the table looks like on table M. So it looks like it shows various resolutions that you would get for the different numbers of trials. So again, for 3, so let's look at 16. For if you have 4 factors in 16 trials, you get that's a full factorial. 5 is you get resolution 5, 2-factor interactions are not confounded with each other. In resolution 4, 2-factor interactions are confounded with the main effects. Excuse me, I said it wrong. So resolution 5, 2-factor interactions are not confounded with the main effects. Resolution 4, you have the main effects are confounded with the 2-factor interactions are not confounded with each other. And then in resolution 3, 2-factor interactions are confounded with the main effects. So anyway, we got this design would be a resolution 4 where 2-factor interactions are confounded with other 2-factor interactions, but not the main effects. So in summary, we talked about creation of 2-level full factorial, and the interactions created a saturated 2-level DOE and fractional factorial design alternatives.